Today we will discuss a new topic, that is the bipolar junction transistor biasing and its stability. Basically, it is a continuation of our previous video lectures. Uh, the part 1 was the working mechanism of bipolar junction transistor. Part 2 is the configuration, the different transistor configuration, and the part 3 we discussed about the application and the exercises, some problems. Here we will discuss the biasing. What is the importance of this, the biasing? It is the familiar, you are familiar with this circuit diagram, that is a common emitter NPN transistor for amplification. We are using the amplification. What is the requirement? That it will enhance the strength of weak signal, that is called the amplifier. So you are also familiar with these curves, that is already we discussed, that is the output characteristics of bipolar junction transistor. There is a three distinct regions we discussed already: the cutoff region, saturation region, and this one is called the active region. So the active region is our interest. Here we plot the load line, which is basically intersect to the output characteristics curves, and the points are called the operating point. So the operating point is the point where we can use for these values are used for the amplification. So here important thing is that the biasing is important, right? So what is the importance of the biasing? That the amplification will be in such that we can avoid the undistorted or distorted the noise of the signals, which we don't want. And the amplification is important when we are using as an audio amplifier, these things. So I'm not going in detail about this in my previous video lectures. If you teach me electronics, this YouTube channel, you can get all the informations in one shot, right? So the DC operating point between the saturation and cutoff is called the Q point. That is the Q point you can see on the load line, which will intersect. Already I told you. The goal is to Q point such that it does not go to the main concern now, that biasing, that this Q point should not go to the saturation region or cutoff region. If it will shift to here or here, then what will happen? We will not able to get the proper amplification. Okay, it should be in the active region. So that is the main concern for us, and you can say that the Q point is the same, should not be shift due to the change in collector current. So that is what is the collector current? IC. We know that IC is equal to beta plus 1 ICBO plus beta IB. You know this formula previously. What is beta? Beta is the current constant, the current emitter gain. That means current gain for common emitter configuration, and that is the beta. And ICBO is, you are familiar with IC is equal to beta IB. We are not concerning with ICBO because ICBO is insignificant. But what is happening when we are considering the the temperature? Temperature is very important factor, which we will discuss in this slide. Then you can understand that what is the importance of the ICBO. ICBO is the reverse saturation current in the collector to base junction, right? And beta is the current emitter, that is the current emitter gain, current gain in the emitter junction. And the change in beta, suppose when we are in a circuit board, generally the transistor, sometimes the transistor will maybe getting some problem. So then what we have to do, that transistor we have to replace. So due to the replacement, maybe beta will change. So that is the another things. If beta will change, then IC will change, because it is related with the beta is related with the IC. Okay, another thing is the temperature variation, which is basically affecting by the ICBO. How it is affecting, that we will discuss. It is a, you can see the reverse saturation current, that is ICBO, is a strong function of temperature. How? I am just showing you through this diagram. You see that the IC is related with minority charge carrier, and ICBO, which is minority charge carriers, is related with the ICBO, and this ICBO is related with the IC. Now, when the minority charge carrier, when the temperature will increase in the system, then it will basically affecting the collector current. So how? That is, the minority charge carrier will increase. So the minority charge carrier will increase means the reverse saturation current, which is responsible due to the minority charge carriers, that will also increase. If it will increase, then obviously if you see the ICBO is directly related with the proportional to the IC, so IC will increase. So IC will increase means again the temperature will increase. So the temperature will increase means the minority charge carrier will increase. So it is a kind of loop. That's why I'm just showing through this diagram. I think it is clear for you that how it is affecting the IC. So the temperature is a very important factor that will basically depending on the minority charge carrier as well as the ICBO, the reverse saturation current, okay, in the collector to base junction, right? So what will happen? The temperature is basically, it is a cumulative effect, and which is basically, we can say it is called the thermal runaway. So the thermal runaway means the temperature of the system of the transistor will increase, and which is it is uncontrolled because of the, it is a kind of loop that we will discuss already in our these slides. Okay, so now we will go to the how we can this is the factors that the thermal runaway we have to avoid, and to avoid these we will go to the stabilization. The stability, how we can increase the stability. So the method to build operating point independent of temperature changes or variation in transistor parameters, that is called the stabilization. So the stabilization is a factor, we will measure it using a factor which is defined as the ratio of change in collector current with the collector leakage current. What is the collector leakage current? That is nothing but a ICBO, that is a reverse saturation current in the collector to base junction. Okay, so mathematically what we can write? S is equal to DIC by DICBO. Okay, so now what we have to do, that lower the value of AS, that is the better stability. So what we have to, whatever the circuits when we will design, our main goal, main objective should be that we have to reduce the value of S. Okay, then we can get better stability of the transistor. Okay, so now what we can do, we have to find out the exact expression, mathematical expression, how the ICBO and the IC is related. Now what are our basic equations? Basic equations is the IC is equal to beta IB plus beta plus 1 ICBO. Now if I will differentiate this expression with respect to IC, that means the collector current, then what we can get, that is the after differentiation with respect to IC, then we can get this. So here DICBO by DIC is the reciprocal of S, so we can write, we can change it. So the simplification is this, so we can write this equation in the simplified form using the concept of S is equal to DIC by DICBO. So we just replace this part, and further simplification we can get that the stability factor is equal to beta plus 1 minus beta DIB by DIC. So now what we happened, that the stability factor, the expression, mathematical expression is this one. So what we have to do, that next slide we will discuss the different configuration, the different circuit, and based on this we can find out the DIV and DIC and how it is affecting, because you know that this is, you can remember that lower the value of S, better the stability. So we have to see that how we can reduce the S, the stability factor. Okay, that is our main challenge. Okay, using the different configuration, circuit configuration. Now, what are the various biasing circuits? That is the proposal is fixed bias or base resistor biasing circuit, then the fixed bias with emitter resistor configuration, then is the collector to base bias circuit. Another, the most important, is the potential divider or voltage divider bias circuit, that is more stable. We will discuss one by one, and also we will discuss here the some problems, that is the circuit problems which is usually providing for the any test, the entrance test, which is very important for the students, right? So now we will go to the fixed bias, the base resistor biasing circuit. You can see here that the main another objective is to that we will use one source, one DC bias source, and that is the DC bias source here, the VCC, which is basically feeding to the input loop as well as the output loop. So the input loop is basically, you know, the base to emitter loop is called the input loop, and the collector to emitter is called the output loop. So here if we'll use the Kirchhoff's voltage law in the base to emitter, then VCC is the bias which is applied, and IBRB is the potential drop across RB and the potential drop across the base to emitter junction. So VCC is equal to IBRB plus VBE. We can write this. So it is just in different way. So from here I can get the IB is equal to VCC minus VBE by RB. So that is a simple expression. So from there we can get the IB. Similarly, the in the common emitter, the collector to emitter loop, that means in the output loop, here if you can see that basically here the VCC is equal to ICRC, that means the potential drop across RC, plus the VCE, that means collector to emitter potential drop. So this will be equal. So if I'll put in this side, then the minus VCC is equal to ICRC plus VCE. Okay, so this is very you are understanding this. Now the question is, what is the role of C1 and C2? You know, that is basically the purpose of using this, that what the AC input signal which we want to amplify, that will only the DC signal will block and AC signal will pass. That's why we are using the capacitor here and in the input port as well as the output port. Okay, so there we will get the pure AC output signal. So that is our main objective. So now here you can see AC is equal to beta plus 1, that is our expression already we derived in the previous slide, and now using these three equations we can simplify it, and then we can get S is equal to beta plus 1 minus beta RC by RB. So that is the final expression. So here you can see if RC will basically very less than, that means this resistance is very less than this resistance, then AC is equal to beta plus 1. So it is not very small value, you know, because beta is generally 50 to 500 times the value. Beta is the, what is beta? Again I am saying this is the current emitter, the current gain in the common emitter circuit, current gain in the common emitter circuit. Okay, so that's why you can say that the stability factor is S is equal to 1 plus beta, if, but this is a very unstable, you can understand. So the advantage, if you see the advantage, that it is a very simple way of doing, that means the circuit is very simple, operating point may be shifted easily anywhere in the active region. That suppose you want to shift the the amplification, if you want to increase the amplification, then you can easily do it by the changing the resistance RB value. Okay, but another thing is that it is I told you the very number of components are required very small, but it has major disadvantage. What is the major disadvantage? That is the circuit is unstable. So because of the unstable means the AC is equal to beta plus 1, the value is very large, and that's why it is unstable. So if the circuit is unstable, then the stabilization is poor, so it can, the temperature will increase or the beta values will increase, so that is not desired for us. So that's why this circuit is a strong chances for thermal runaway. So we cannot resist if we'll use this. So what will be the solution for this? The fixed bias circuit, what we can introduce? We can introduce some other components, that is the next circuit. But before proceeding on that, what we will discuss a problem. The problem exercise is a fixed bias circuit using an NPN transistor circuit. So here the determine the values of base current. The base current means IB, IC collector current, and the collector to emitter voltage VCE. Okay, so they have given the parameters values. So from here we can find out the value of base current. Here, since this is not saying any that what types of transistor, or they have not mentioned the VBE, the potential drop across the base to emitter junction, so we can ignore this part. So if here the KVL, the Kirchhoff's voltage law, if we will use this, then VCC is equal to IBRB, right? The VBE is not given, means it is, we can consider 0. Okay, so that is the value. So IB we will get 166 microampere or 0.166 milliampere. So after that, what we will do, the value of collector current. The collector current, you know, this is a very important, the formula already I discussed, that is the beta is the current gain in the common emitter circuit. So from there we can get the IC is equal to beta IB. So IC you can get easily from this. Now here the IC, if you'll get IC and IB, so IC if you'll get it, then the Kirchhoff's voltage law in the output loop if you'll consider, then VCC is equal to ICRC, the potential drop across RC, plus VCE, that means collected to emitter voltage. So here the VCE is equal to how much you are getting, that is 17.78 volt. So it is easily you can find out the values of the collector to emitter voltage as well as the collector current and base current. So these all values you can easily find out from these problems, right? So I think it is clear for you students. If you have any queries, you can ask me. It is given here, my mail ID, so you can drop a mail. I can give you the more clarification if it requires. Okay, next is that the fixed bias, we have to do some modification of the fixed bias circuit. Here I am just doing the modifications, that in the emitter port, which is directly connected with the ground, but here we are just doing some small modifications, that is the emitter resistance, we put the emitter resistance. What is this, the role of the emitter resistance here? That is it will create a negative feedback. So the negative feedback will give some the stabilization of the Q point, so it will not shift. Okay, so that will basically given you some stabilization, more stabilization. So this is the advantage, that it is tendency to stabilize the operating point against changes in temperature and beta value. So we can resist, but it is not a good solution, because you can see here the beta value is fixed for a given transistor. This relation can be satisfied by keeping RE is very large. So then only we can do it, or making RB is very low. So because it is a kinds of ratio between RB and RE, so that's why if the RE is very large, then only you can get the effect or the advantage, or better to otherwise the RB will be small. So this is very some conditions we have to apply if we can use the fixed bias with emitter resistor. Next, we will discuss the third one, that is the collector to base bias circuit. In the collector to base bias circuit, the main thing is that in base, the previous one, the fixed bias circuit, we are using the VCC directly to the input loop as well as the output loop. But here you can see that RC is common in both input and the output loop. That is the one thing is very important, and this is, you have to notice this part. The configuration employs the negative feedback to prevent thermal runaway and stabilize the operating point. So that is important here, the negative feedback, the role of negative feedback here. That's why it is just given the RC is common in both input and the output loop. Okay, so here the in the applying the KVL in the input loop, you can understand that here the input loop means this one. So here this is the input loop according to the Kirchhoff's voltage law, VBE, that is the base to emitter potential drop, and the IBRB is the potential drop across RB, that should be equal to the collector to emitter potential drop. Here we are not considering VCC because of that VCE is equal to a VCE is the potential drop across the collector to emitter, that will be reflected to the input loop. Okay, so and in the output loop, what is happening? In the output loop, VCC is equal to the potential drop across RC, that is IC plus IB into RC plus the collector to emitter voltage, VCE, right? So this part is okay. Applying these two equations, if we will simplify this, then we can get IB is equal to these values. Okay, now you can, it is a simplification, you can do also yourself. So you will get that IB is equal to VCC minus VBE minus ICRC by RC. So we using these equations, and we have these equations, and another equations we know that IC the S is equal to the IC is equal to beta IB plus beta plus 1 ICBO. We know these equations. So using these two equations, what we can write that we will get that it will be IC is equal to beta VCC minus VBE. Just using these two equations we will get it. So this is, I think it is, you can do yourself also. Now we have to find out the S, the stability factor. Now S is equal to, you know, the beta plus 1, the previously what we derived, beta plus 1 divided by 1 plus DIC by DICBO, sorry, DIC by DIB beta into, so that is we can put here. So we will after simplification you have to derive this using the same equations which we derived in the stability factor derivation. So then you will get the expression, that is beta plus 1 plus beta RC. So you can get it easily. So from the above expression, what we are getting, the denominator has a significant term. We cannot ignore the denominator term. So the denominator, if the denominator term will be significant, then basically we cannot, it is less, the bias is S is equal to, the value will be not beta plus 1, it is smaller than beta plus 1, right? So and also if RB, you can see that RV is very less than RC, that means the output impedance will be more, then S is equal to 1, the stability factor will increase. So that's why this is the advantage, is the better stabilization compared to fixed bias. So what are the disadvantage of this? The circuit provides negative feedback which reduces the gain of the amplifier. So sometimes the gain means what we are given as an input and what we are getting as an output. So that will basically determine the gain of the amplifier. So that is, we have to sacrifice the gain because we are using some negative feedback circuits in the collector to base bias. Okay, so that is the collector to base bias. Now we will switch to voltage divider bias circuit. So what are the voltage divider bias circuit? It is a very stable bias circuit, I told you already, and the currents and voltages are nearly independent of any variations in beta. So that is the important things, that here we will do the circuit, that is you know, there is R1 and R2, we are using the two resistance instead of one, the base resistance, and the rest of the term is the same. Here we are using the RE also, the emitter resistance. C1 C2 is generally for the blocking of the DC things, so that is not important for us. I mean we will use this, we know. Now we have to do the simplified form of this because here the Thevenin's theorem, that is the circuit theorem, you know, there we are implementing here. So before proceeding this one, we will just simplified form of the same. We can say R1, R2, RC and RE. So this is the NPN transistor. So that is the simplified form of the circuit. So here the R1, R2 means we have to understand. So here we will use the Thevenin circuit theorem. So if we will use the circuit applying the Thevenin's theorem, what we can get, the this is the circuit diagram, the equivalent circuit. This is the equivalent circuit. Here we can see that RTH is the Thevenin's resistance. So it is just, you can see here, this is the parallel combinations R1 and R2. So it is a parallel combination. So you can get the R1 R2 by R1 plus R2. And similarly the potential drop, that is the VTH, what we can get it, VCC, this is the R2, this one is the R2. So R2 VCC and the total resistance across the input loop. So that is we will get VCC into R2 by R1 plus R2. So after simplifications, base to emitter loop, here we can do using the applied Kirchhoff's voltage law, then we can get these things, and from there we can get the IB, and similarly collector to emitter loop, there we can get the IC. So these two values we will put, then we will get the after that we know that is, so we put the value of DIC by DIB. So there we can get the equation something like this. So this is the equation where RT is equal to R1 R2 by R1 plus R2. So in these equations you can understand that beta plus 1, here these terms are very significant. So if this term will significant, obviously the A's value is very less, and since the A's value is less means the circuit is more stable. So that's why the voltage divider circuit is more prominent, and the operating point is almost independent of beta variation. That is the first advantages of this. And again another advantage is operating point stabilized against shift in temperature. So the beta and the temperature, these two points we can solve when we are using the circuits, that is the potential divider bias circuit. What are the disadvantages of this? That beta value is fixed for a given transistor. So that means this relation can be satisfied either by keeping Re fairly large or making R1 R2 very low. So that is again the same like collector to base bias what we discussed so far. The same things are implementing here. So what we have to do, that another thing is that if Re is of large value, then high VCC is necessary, and which is increases cost as well as the precautions necessary. So we can sacrifice about this, because here we can make the beta variation independent of beta variation. That means it is irrespective of the beta variation as well as the temperature. The temperature. So these 2 points we can compromise, or we can sacrifice, we can avoid easily when we are using the potential divider bias. Now the questions, there is some exercises of the potential divider bias. You have seen this is the equations are given here, and this is the determine the value of collector current and collector to emitter voltage. That is for your understanding. Here you can see this is the circuits and all the values are providing here. So now what we have to do, here you can see that VVE, that means the base to emitter voltage, the 0.7 volt, it is mentioned here. So you can understand that is nothing but a silicon transistor. So these values are given, means you have to use this value. So determine the collector current. What we can do, that we know the base voltage is VV. VV is basically nothing but a VTH. The Thevenin's, here we have to use the Thevenin's theorem. So VCC into R2 by R1 plus R2, the potential drop across R2, that we have to set the base voltage, that is the Thevenin's voltage. From the Thevenin's voltage we can, after simplification of the circuit, we can use this. So then the voltage at the emitter, what is the voltage at the emitter? VE is equal to VV minus VBE. So from there we can get the values this, and you know that VE is the emitter voltage. So emitter voltage, if we'll get it, then we can find out the emitter current, that is nothing but a VE divided by the across the RE, the potential drop. So from there we can find out the Ohm's law. Using Ohm's law we can get the IE. Now since there is the IB, the collector current, the base current is very insignificant, because you know that base current we are getting the in microampere range. So we can avoid these things. So what we can write then, we can write IC is equal to IE. Okay, so that is IC is equal to IE. So the collector current IC is equal to IE. So it is almost the same, because it is insignificant, as IB is in the microampere range. So the microampere range and milliampere range, you can know that, you know that there is a 10 to the minus 3 variations are there. Okay, so the collector to emitter voltage of VCE is equal to VCC. That means we are applying here in this side the output loop, the KVL, the Kirchhoff's voltage law. Then we can get the answer is 2.11 volt. So the collector to emitter voltage we can find from there. And so I think this is clear for you. And next, another problem, there they determine the DC bias voltage VCE and the current IC for the voltage divider configuration. So this is the circuits are given, and here we will do the IB, and I want to show you that how the IB, I told you in the previous slides that IB is insignificant compared to the IC and IE. That is, I just show you here 6.05 microampere. You can see it is in the microampere range, so it is very less. So we can ignore this part when we are considering IC and IE. But here we are considering this because we have to find out IC. So that's why IC is equal to beta IB. So from there we can find out the IC value easily also, because we can go, this is another approach that we are not going to IE. So this is another approach I am showing in the two approaches, such that you people can understand that this is also right, the previous one also right. So there, after that we can find out the collector to emitter voltage, that is 12.22 volt. So this is KVL, using the KVL, Kirchhoff's voltage law, in the output loop, then we can find out the value. So this is the analysis of the different circuit diagram of the amplifier circuits. So I think this is clear. If you have any queries, any doubts, feel free to ask me in my mail ID, through my mail ID. So this is a comparison of basic bias circuits. Here you can see the base bias, collector to base bias, and voltage divider bias, which we discussed in the slides, that is just given here. And I think if you'll gone through on that, the same things which we discussed so far, that is just given in a tabular form. And so what is the conclusions of today's discussion on biasing? The Q point is the best point for operation of a transistor for a given collector current. So it is the things what I started the previous two slides, the first two slides we discussed on that. The purpose of biasing is to establish a stable operating point. That means the operating point is stable, means it should not be shift, and it should not be going to the saturation region or the cutoff region. It should be in the active region. So that is the challenge, and for that the two factors are very much important. One is the temperature, another is the beta. So beta is related with the transistor when we replace the transistor or in the circuit, or the temperature is basically related with the collector current. So it is a cumulative effect, and it is called the thermal runaway. We can avoid these two if we can use the proper biasing. That is the voltage divider bias, the most prominent one we discussed in our study. Okay, so I think it is clear for you. So we will conclude here. So that is our patient hearing, and feel free to ask any questions through email, no problem. So please understand the things clearly. Thanks.